Okay. Right. So now we're recording. Okay. So, so what is the intersection here? The intersection here is just one of these events, which is a subset of the other, and that is a green event. Okay. And this is equal to, therefore, the probability that capital X is less than or equal to pi. And what is that probability?
1/2.
1/2. Right. So we're talking about the numerator here, right? So don't forget that. What about the third case? Third case is when क्या रह गया? So I've talked about the case when 0 से छोटा है. I've talked about when it's greater than pi. What we're left with is when small x is less than right this case here, right? And I'm interested in finding what the probability of the intersection of these two events are, right? So what would this be equal to? If I look at the number line, now, what I have here is this is 0 and this is pi, and where's x? Small x is here. And this is the probability, or this is the event that capital X is less than or equal to small x. And this is the event capital X is less than or equal to pi. What is the intersection? What is the intersection of these two events? Mohsen, do you have a question or do you want to answer? Yeah, pehle ka
Sir, answer.
Yep, go ahead.
So the CDF evaluated at X.
Right.
और सर एक और क्वेश्चन था.
अच्छा, हाँ, sorry, ठीक है, आप सही कह रहे हैं. Sorry, you have the right answer. Yeah, question.
सर x is less than pi नहीं होगा इस केस के अंदर, और ऊपर सेकंड केस में less greater than or equal to pi होना चाहिए.
Yeah, so remember, I mean, does not really matter. Why? Because we're talking about a continuous random variable. Okay, so I may be careless in how I'm using inequality. So, and the reason is because it does not matter. The reason is because it does not matter. Okay, because the probability of a continuous random variable being equal to something is 0, right? So whether I have an less than equal to there or whether I have a less than there, the probability stays the same. Had
Right,
this
sir.
been a discrete random variable or a mixed random variable, we would have had to be careful. Okay? All right. So this is just simply equal to the probability that capital X is less than or equal to small x, which is nothing but the CDF evaluated at small x. Right? Now I have all of the information to be able to write out what this CDF is, what the conditional CDF is. So my answer is, so f x given a small x is equal to, and I would have to define three cases here. The first is going to be 0 whenever small x is less than or equal to 0. What about the second case? Where second case is when when 0 is less than x is less than or equal to pi. Right? यहाँ पे क्या आएगा? So this is f x of x times 2. Right? And which is actually, let me plug in what fx of x was. Remember, fx of x was 1 upon 2 pi x. Right? So this was x upon 2 pi. Right? And therefore this becomes equal to x divided by pi. Why is it x divided by pi? Because there's a half here. Remember, there's a half here. Okay, so that half cancels with 1 upon 2 in the pi here, and moreover this is 1 for x is greater than pi. So this is your answer. Okay, this is the solution. Right? Now, what does this mean, by the way? I mean, what kind of a CDF are you talking about? What kind of a random variable is this new random variable going to be conditioned on the event A? क्या कह सकते हैं? जी शोएब?
It's still a uniform random variable.
Still a uniform random variable, but not the same random variable as the original one, right?
Yes.
How
yes.
is it different?
So उसमें gradient जो है, I don't remember क्या था, but इसमें जो gradient जो है between
Yeah.
0 and pi, that is different.
Yeah. And so is gradient is different. What is, and why is that so? Gradient किस लिए
Okay.
change हुआ असल में?
आपका total probability बन रहा है.
हाँ, लेकिन असल में कुछ observation थी ना. देखिए, original random variable could be anywhere between 0 and 2 pi. जी Maz, you want to say
Yes.
something?
जो इंटरवल चेंज हो गया हमारा 0 से पाई का.
जी, say again.
इंटरवल चेंज हो गया हमारा, पहले 0 से 2 पाई था.
Good. Interval change हो गया, right? So originally the random variable was between 0 and 2 pi, and it was uniformly distributed there. Now, condition on somebody telling you that the random variable has been observed to be between 0 and pi, the new random variable still is uniform except that the interval changes, right? Or the length of that interval changes. Now it's a uniform random variable between 0 and pi, and that's why the gradient actually changes. Okay? So based on this analysis, what we can conclude that this actually corresponds to a uniform random variable, which is uniform between 0 and pi. Okay? So strictly speaking, Mohsen, what you were saying is correct. So I'll correct this in my notes when I upload them later. Okay? So I should have the other way around equalities. Okay? All right. Any questions here? Before I generalize this a little bit. And this generalization is let the event A, which is an observation, be that the random variable is not only upper bounded by something, but it's also lower bounded by something, right? So this is A is less than X is less than equal to B. Let's say this is something that you've been given, right? So this is a conditioning, or this is an event that we've observed, right? That the random variable lies within the interval A and B, right? Now, conditioned on this event, we wish to find out what the CDF of the new random variable was, right? Or the conditional CDF is. So that's what we want to find out, okay? So given fx of x, you need to determine the conditional CDF. Okay. Now, how do I go about this? That's pretty much what we did in the previous example with a slight bit of a modification or generalization, right? So this is defined as a probability that x is less than equal to small x, and a, which is this a is less than x, is less than equal to b, and divided by the probability that a is less than small x is less than equal to b. Right, so I've skipped one of the steps and written this directly here, right? Now I can divide this up into several cases, right? So just like I did in the previous example, what should those cases be, right? So the first case, of course, is when x is less than equal to a, right? What happens here? What happens here? G. Mohsen?
So the intersection would be a null set.
So an intersection would be a answer. So the probability that capital X is less than equal to small x and A is less than capital X is less than equal to B, that's 0. Right? So you take the intersection is null, right? And therefore the probability is going to be 0, right? Similarly, I can do, what about the case when X is greater than B? What is the probability that capital X is less than equal to small x? A is less than X is less than equal to B. What is this equal to? The somebody else, the Salman.
This will be equal to 1, sir.
It's not exactly equal to 1. So this is normalized 1 है, I agree. लेकिन थोड़ा सा और सोचें. So you can sketch this out if you wish, right? So if I sketch this out, see, ये A है, ये B है, right? And this is the event that A is less than capital X is less than equal to B. ठीक है? And what about the other event? Or small x किधर है? Small x is somewhere over here. That's it. This is small x, right? And this red thing, this is the event that capital X is less than equal to small x. इन दोनों का intersection क्या है? I mean, what is the common thing in there?
So the area between A and B.
The area between A and B. Very nice. ठीक है? So this is the area between A and B. So this is therefore simply equal to the probability is A is less than X is less than equal to B. ठीक है? No matter what small x is, as long as that small x is greater than B. Okay? Now what about the third case? Third case क्या रह गया? सलमान नदीम बताएगा मुझे.
Sir, between A and B.
Between A and B. So when A is less than small x is less than equal to B, what will this probability there be? What is this equal to? G. Monson?
So the PDF, the CDF evaluated at X minus the CDF evaluated at A.
Okay, so I'll rather write this out in probability terms, which is A is less than capital X is less than equal to small x, right? So small x is between A and B. तो उन दोनों का intersection लेंगे, so the intersection is going to be between A and small x now. ठीक है? So for the third case, this is what you're going to get. Okay, which you're right is equal to. So let me write this out as you suggested. So this is the CDF evaluated at small x minus the CDF evaluated at A. And what about this case? This is the CDF evaluated at B minus the CDF evaluated at A. Right? Now I have all of the information to be able to write what the conditional CDF is going to be. Right? So the conditional CDF fx given A is going to take on 3 functional forms. The first is that it's going to be equal to 0 whenever small x is less than equal to A. Okay? What about the case when A is less than X is less than equal to B? इसमें क्या होगा? So the numerator is what? The numerator is fx of x minus fx of A. What about the denominator? This is what the denominator is, right? So what is this denominator? So what is this denominator equal to? Said, you want to take a go?
Sir, fx of b minus fx of a.
Excellent. Right. So this is fx of b minus fx of a. And then I have the third case, right? So the third case is going to be equal to what? The third case is this divided by the denominator, which is exactly what this numerator is, right? So the third case is when x is greater than b, and this is 1 in that case, right? So these are the three cases. Okay, so this is a conditional CDF. Okay, any questions here? So conditional CDF for this particular conditioning event, right? The conditioning event could be of other forms as well. Okay. Ji Isha.
Did I misunderstand that greater than b, it won't be equal to 1?
So greater
उस
than
वक्त
b.
आपने कहा था that it doesn't exactly come out to be 1.
So for greater than b, it flats out at 1. आपने 2 pi कहा था.
नहीं सर, अभी थोड़ी देर पहले when you were discussing this, I perhaps took it wrongly then.
फिर से बताएं कि what did you understand?
सर उस वक्त जब ये डिस्कस हो रहा था तो मुझे ऐसा लगा था कि आपने किसी और क्वेश्चन पे कहा है कि it doesn't come out to be 1 exactly.
I don't recall कि
I think ये second case में बोलिए जिसमें आपने बोलता कि exactly 1 नहीं होगा, normalize होके 1 हो जाएगा.
Oh yeah, so the numerator.
Exactly.
So the numerator in the third case is not 1, right? So
oh, okay, yes.
So somebody
right.
said
okay.
कि
Now it clarifies.
Somebody said कि yeah, this is going to be equal to 1. This probability is going to be. This is not 1.
Okay. Yes.
But
okay.
Divided by the denominator, then that's 1. Okay. Right. So
yes,
this.
It's clear now.
Right. So this is the. And let me leave it like this here. This is, remember, for the case when the A event was A is less than capital X is less than equal to B. Okay. Now we want to talk about conditional PDF. So those are easier to handle, by the way. And the conditional PDF by definition is limit epsilon going to 0, probability small x is less than equal to capital X. So actually x plus epsilon given A divided by epsilon. Right? So this is the definition of conditional PDF, and you can immediately see that this is nothing but the derivative of the conditional CDF. Okay, so there's a direct relationship between the conditional PDF and the conditional CDF. Isha, do you still have a question?
No, sir. I'm sorry. I forgot to lower my hand.
Right. So the relationship between a conditional CDF and a conditional PDF is that of a derivative and an integral. Okay, and you can reduce all of those properties that we have for PDFs. Those are applicable to conditional PDFs as well because they're valid PDFs. The area under the curve of a conditional PDF should always be equal to 1. The conditional PDF must always be greater than or equal to 0. Why? Because a conditional CDF is a non-decreasing function. Okay. The probability that a random variable is between A and B conditioned on A is just the integral or the area under the curve of the conditional PDF from A to B, right? So all of those definitions still apply. Okay, so I'm going to skip on those details and because they're pretty straightforward. Okay. What about this particular case जो अभी हमने ऊपर देखा है, right? So for the example above, with the condition event being of this form, a is less than capital X is less than equal to small b. What will the conditional PDF look like? So who's going to help me here? So all you need to do is क्या करना है? So what do I need to do? D Mohsin.
So it would be a uniform distribution between A and B and 0 otherwise.
Not necessarily. I mean, nowhere did I tell you. So when I say the example above, this is the example I'm talking about. So this is the example I'm talking about. Right. So the original PDF is generic, is not necessarily uniform. Okay. So up, given that the conditional CDF takes on this form, which is given by equation 1, what will the condition PDF be? So conditional PDF, I know by definition is just a derivative of the conditional CDF, right? So all you need to do is differentiate equation number 1 with respect to what? Josefa?
So we'll differentiate the first equation with respect to x.
Yeah. So what do you get when you say that?
The first one is gonna be, I mean, for x is less than a, it's gonna be 0, and for x is greater than b, it's again gonna be 0.
Got it.
And for the interval, we're basically gonna have like a small f.
Yeah.
Like instead of all the capital F's, we'll have like small f's on each.
Okay. So what you're saying is कि ये होना चाहिए fx of x minus fx of a divided by fx of b minus fx of a. Is that what you're saying?
So I'm not exactly sure if this is going to be the case, or if we're going to like derivate the whole expression in
Yeah. So
terms of
see, this is not the case. This cannot be, because there's a fundamental concept which we need to incorporate, which is you're differentiating with respect to small x. So the variable is small x. ठीक है, the variable is small x. बाकी सारे के सारे जो ये चीज है, this is not a function of small x. This is not a function of small x. This is not a function of small x. Rather, they're just constants. Small a is a constant, small b is a constant. This is just a function evaluated at that small a. That's the function evaluated at small b. The derivative of that with respect to small x is 0. Okay? So as far as differentiation is concerned, I mean, all of these three things highlighted here, they're actually constants. ठीक है? तो फिर इसका derivative with respect to x क्या होगा?
So like small f of x and the rest are going to be just the same. Like,
yeah, but जो minus वाली term है वो तो नहीं रहेगी, right? So you see, this is the derivative of fx of a given x, right? So this is, as you rightly said, this is 0 for x is less than or equal to 0. That I agree. Similarly, this is equal to 0 when x is greater than b, right? But now what about the middle term? Middle term needs to be differentiated with respect to small x. So this is just
small x over,
yes, divided by, this is a constant.
Yes.
Right? Remember the second term goes away because that's also a constant. Okay? So this is a is less than x is less than or equal to b. Okay? So, and I therefore don't actually need to write this anymore in terms of these three cases, because I know it's 0 outside of this interval, right? So this is just, if I can mathematically write this out very, very nicely, which is KR, this is, there are two ways I can do it. This is equal to fx of x divided by, I can say this is a probability, is just a normalization constant, times u of x minus b minus u of x minus a. Right? So the PDF only is non-zero or between in the interval from A to B, and is 0 outside of it. Okay, so this PDF is much, much easier to handle. So when you condition on a certain, the random variable being on a certain interval, what happens with the conditional PDF is कि वो conditional PDF की shape उस interval के अंदर वही रहती है, except is scaled by some constant, and outside of that interval just goes to 0, right? So as an example, so for example, so let's say you had this CDF. The original CDF looks something like this, right? This is fx of x, right? And this was some A, and this was some B, right? Giuseppe, you have a question?
Sir, won't the step function be u of x minus a minus u of x minus b?
B is greater, right?
So like,
sorry. Take it. Sorry, no, you're right. So B is greater. Thank you. ठीक है? So A से B के दरम्यान में this is equal to 1 and 0 outside of this. Okay. So graphically speaking, so if this is small a, if this is small a and this is small b, right? What would the conditional PDF look like? The conditional PDF would be 0 outside of this interval A and B. So इससे बाहर हर जगह पे 0 होना है, right? And inside of it, this is going to be the same shape as the original PDF, except that it has been scaled by some constant in order to ensure really that the area under the curve stays 1. ठीक है? तो ये बाहर क्लिपिंग हो गई और यहाँ पे एकदम से ये बढ़ेगा, right? And the shape is going to be like the same shape as the original. And then it goes. So it looks something like this. And the scaling, by the way, is always going to be with a number which is greater than 1. In other words, it's going to be scaled up, right? And why is it a scale up? Because, I mean, it must be scaled up to ensure that the area under the curve stays 1. Okay? So when the conditioning on a random variable is of the form that is in some interval, right? These CDFs are slightly more complex looking, if you will, right? So you have to have different cases for that. But the PDFs are much, much easier to define, right? It's just the same PDF, the same functional form within that interval, except that it has been scaled up. Okay? And we've actually proved this. We proved this through this entire process, right? So just don't take my word for it. If I give you some other variations of this interval, right? Go ahead and try to derive it, starting from the conditional CDF and then taking the derivative and then coming up with, as you would have to do in homework 1. Take the last problem of homework 1, actually. Okay? So don't remember any formulas per se, right? Rather, always remember where things come from, and that's going to be extremely helpful in the long run. Okay. Let me do another example, this time with the Gaussian PDF, actually. So this is another example. So you're given a Gaussian random variable, which is actually a zero mean Gaussian random variable with variance sigma squared. Okay. And I ask you to find the conditional PDF of x given that x is greater than 0. So having done all of this analysis, having done this analysis which is up there, okay, what will this be equal to? Ji Maha, can you help me here? Maha, आपका mic तो unmute हो गया, but I can't hear you. Okay, so anybody else? Maz? Maz, can you hear me?
Yes, sir.
Maji. So how do I go about this?
इंटरवल जो हमने जनरल डिफाइन किया है उसमें तो दो लिमिट्स हैं, इसमें भी
Yeah.
हम लिमिट डिफाइन कर सकते हैं कि ए इट विल बी द इंटरवल वुड बी के प्रोबेबिलिटी
एक मिनट. So Maz, हमने जो ऊपर वाली जो चीज डिफाइन की है वो that's between A and B. Okay. Can I not think about this interval, which is x is greater than 0, as a special form of the one above? In other words, I can say that this actually corresponds to B something.
Sir, B infinity होगा उसके इसमें.
Okay, exactly. So this is nothing but the form that we've already seen. Right? So A is less than capital X is less than B. If B is infinity, that just means that X is greater than 0, or X is greater than A, which A is in this case is 0. Okay? So this will be equal to, therefore, is fx of x divided by the probability that x is greater than 0 times u of x. Right? And what is the probability that x is greater than 0? Is a Q function, right? Which is 0 minus the mean. The mean is also 0. So this is 0 by sigma squared, sigma, sorry, 0 divided by sigma, doesn't really matter, by the way, which is Q of 0. What is Q of 0?
Half.
That's always half, right? Because of the symmetry, right? So 0 is centered, and it's as because it's symmetric around 0, this must be half. Okay? So this is actually equal to, I'm skipping a step here, so this is half ऊपर चला गया. So this is 2 divided by pi sigma squared e raised to power minus x squared divided by 2 sigma squared u of x. ठीक है? Is this a Gaussian PDF? I mean, can I say that this is a Gaussian PDF? Isha, can I say this is a Gaussian PDF?
Sir, I think you can.
You can? So this is fx given a of x. What does it actually look like? This is what it looks like. This is 0 here, then it suddenly jumps up, and then takes on that bell curve, if you will. Check.
So it isn't.
So this is not a Gaussian PDF. Gaussian PDF, by definition, has to have infinite support from minus infinity. It has to be negative and it has to be positive as well. Okay, so this is not a Gaussian PDF. Although I could say, could you for values of small x which are greater than 0, the shape is like a Gaussian. I mean, it's still a bell curve. It's just normalized. Okay, but overall, it's not a Gaussian PDF. Okay. All right. Now, let's do another example for actually B part, which is what is the conditional PDF of x given absolute value of x is greater than 3. So what is this going to be equal to? You can go ahead and do all of that analysis up above, and you will conclude that this actually turns out to be equal to fx of x divided by the probability that absolute value of x is greater than 3. And let me write it like this. For all values of absolute small values of small x, whose absolute value is greater than 3 and is 0 otherwise. Right? So what is the probability that absolute value of x is greater than 3? What is this equal to?
Probability of x less than -3 and x greater than 3.
Yeah, so this is what the area under the curves that you're looking for. Right? This is 3 and this is -3. What is this area in terms of the Q function? G Mohsen?
So Q of 3 or the total area आपका twice हो
Q
जाएगा.
of 3 upon sigma. Remember, there's a sigma there.
Yes.
Okay, because this is not standard normal. What about this? This is because of the symmetry. This is also Q of 3 upon sigma. Right? And you just add them up, and therefore we conclude that this is 2 times Q of 3 upon sigma. Okay. Okay. So you just plug that in over there in here, and you'll get the conditional PDF. Conditional PDF के साथ दिखेगी. This is what it's going to be. So what is this going to look like? Anyone? Gmaz?
तो ये -3 मतलब माइनस इन्फिनिटी से -3 तक होगा, फिर 0 और फिर 3 से वापस शेप आ जाएगी.
Good. Right. So ये नीचे जाएगा. Right. And then it's going to stay 0. And then at 3 it's going to go up. And then like this. Right. So this is 3 and this is -3. Right. So this is what it's going to look like. This is the conditional PDF. Yeah. Right. Okay. Any questions here? Right. So there's one thing I want to say. Just actually, let me go back and talk about. Right. So there's one example. Let's do this. Okay. So this is actually from the textbook, and it's actually slightly modified from the textbook, which is this modeling failures. It has to do with modeling failures of electronic components, right? So let's say you buy an equipment from an electronic store, and it has a certain lifetime, right? And it's going to fail after a certain number of years. And when it fails in the number of years that we say is the lifetime of that electronic component, and that is a random variable. We don't know exactly when it's going to fail. Okay, let the random variable be capital X, right? That's the failure time of electronic component. Failure times are typically modeled as exponential random variables. Okay, they're typically modeled as exponential random variables, and for this particular electronic component, this is the PDF that models the failure time of a particular electronic component that you're buying. Okay, this is an exponential distribution. Okay, so exponential recall किसना दिखती है, right? So the exponential PDF is a positive random variable, and that makes sense because lifetime has to be positive, right? Would, by the way, a Gaussian random variable be a good model for the failure time? I mean, somebody just says, "Yeah, I've used a Gaussian random variable to model the failure time." I mean, what would you share with that person? G. Mohsen.
No, sir, the time cannot be modeled as a negative entity.
Right, so the failure time cannot be modeled as being negative, right? So it always has to be positive. So the Gaussian is not a good model for that, right? And it turns out the exponential model is a good model for that. And it makes sense because the failure time, the probability that you're going to fail early on, right? That's higher, if you will, right? So, and okay, so up conditioning क्या दी गई है? Conditioning दी गई है कि यार you've had the equipment for 2 years and it's still working, right? So you bought the equipment some 2 years ago and it's still operational. Now somebody says कि यार, what is the PDF of the failure time given that it hasn't failed yet, right? And what is the probability that it will fail in the next 4 years, right? 2 साल गुजर गए, अगले 4 साल में fail होने की probability क्या है, right? That's something we wish to evaluate, right? So there is a conditioning here, first off, right? And based on that conditioning, we need to evaluate a conditional PDF. What is that conditioning here? What form is that conditioning? In other words, what is that event A? Anyone? So what you're given is that it's still working. Still working का क्या मतलब है? G. Mohsen?
So that the time has exceeded 2 years.
Time has exceeded 2 years, but what can I say about the random variable? So if somebody says, yeah, it's still operational after 2 years. So what is the information that that person is giving me upon capital X? I mean, you're right. उसको capital X terms में किसी तरीके से लेके आए, and try to connect it to what all of that intervals that we've talked about.
Should be X would go from 2 all the way to infinity.
Yeah. Okay. So this is the conditioning is because it's not failed yet. That means the failure time is going to be somewhere between 2 and infinity. Right. So that's what you're given. And somewhere between 2 and infinity just means that the failure time is actually greater than 2. So the conditioning that you're given is that capital X is greater than 2. Right. And I'm measuring X in years. Right. So the average year is 3. So that means the mean failure time is actually 3 years. Right. So even though we've not talked about mean yet, but in some sense, this is the average failure time. Okay. So the condition event is A, which is equivalent to capital X is greater than 2. Okay. Now, what is this equal to? right? So how do I go about this now? जी मौसम
सर ये जो लास्ट एग्जांपल का आपने करवाया था उसी तरह का है कि जी
exactly
PDF divided by 1 minus the CDF evaluated,
right? So this is just fx of x divided by probability that x is greater than 2 multiplied by u of x minus 2. Okay, 2 onwards all the way up to infinity, right? What is the probability that x is greater than 2? Can somebody evaluate this for me? Right, so this is just the integral, right? So this is just the integral from 2 to infinity of what? 1 upon 3 e raised to power minus x by 3 times dx, right? And this is just equal to e raised to power minus x by 3, and this is 2, and this is infinity. I'm sorry, I'm skipping some steps here. This is e raised to power minus 2 by 3, right? And you can clearly see this makes sense. I mean, if this was 4 years, this probability would have been smaller. Okay? And that makes sense. The probability that it's still operational after 4 years is smaller than the probability that it's still in operation after 2 years. Okay? Achha. So if I just plug this in back, so this is, therefore, this is e raised to power minus 2 by 3 times 1 by 3 times e raised to power minus x by 3 u of x minus 2, right? And I can just slightly manipulate this even further. So 1 upon 3 e raised to power minus x minus 2 divided by 3 times u of x minus 2, right? Which is just simply, right? The original PDF, I mean, in this particular example, this conditional PDF is just the original PDF shifted by 2 years. ठीक है? Just shifted by 2 years. उसके implications क्या है? क्या implication, can anybody try to guess? There's the profound implications of this, and this is why exponential random variables are also important. There's a certain property that's satisfied, and we can try to find out the implications. Let's say in the B part, right? The B part is what is the probability that it will fail in the next 4 years, right? So you're saying कि 2 साल गुजर गए और 2 साल तक अभी तक fail नहीं हुआ, and you're required to find the probability that it's going to fail in the next 4 years, following up on the 2 years that have already passed, right? So this is, you're interested in finding what? You're interested in finding what is the probability that x is greater than what? 2 साल गुजर गए और अगले 4 साल में फेल होना के बाद फेल होना, राइट? 4 साल तक, या सो 4 साल के अंदर फेल होना, राइट? व्हिच इज व्हाट? जी मॉज
6 होगा, 6 होगा
सॉरी, फिर से कहिए.
सर 6.
Yeah, so it's less than 6, right? Because I'm required to find the probability that it fails in the next 4 years, given that it has not failed up until the second year. So that means 2 साल गुजर चुके हैं, अगले 4 साल में होना है, तो इसका मतलब failure time is between 2 and 6 years, right? So given that x is greater than 2, given that I've observed that x is greater than 2, ठीक है? Somebody had a question or somebody raised a point.
नहीं सर, ठीक है.
ठीक है? Right. So then you just evaluate what this probability. What is this probability? This is just simply equal to the integral of f(x) given a of x dx, right? From where to where? I mean, you could say that this is from minus infinity to 6, right? Right, because the probability that capital X is less than 6 is integral from minus infinity all the way up to 6. It's just that the PDF is only non-zero between, I mean, from 2 onwards. Okay, so therefore, this is equal to integral from 2 to 6, and this is 1 upon 3 e raised to power minus x minus 2 divided by 3 and dx. Right? Yeah. Right? You compute this integral, and you will find, and I'm skipping some steps here, you will find that this turns out to be equal to 1 minus e raised to power minus 4 by 3. And some of you may be able to see directly. Integral chain of variables कर लें, तो integral 0 to 4 चला जाएगा, and this is what you're going to get. Right? So this is the probability that x is less than 6 given x is greater than 2. But interestingly enough, this is the same probability that x is less than 4. Right? Go ahead and evaluate this probability, the probability that x is less than 4. And you will find that this probability turns out to be exactly the same as this thing. ठीक है? उसका मतलब क्या है? इसका मतलब ये है कि if the electronic component has not failed in the first 2 years, the probability that it's going to fail in the next 4 years is exactly the same as the probability that it would have failed in the first 4 years after you bought it. And this is called the memoryless property of exponential random variables. Right? कि जो पहले हो गया उससे बहुत ज़्यादा उसको memory, there's no memory there. Right? So it's memoryless. Given the fact it has not failed up until 2 years, the probability is going to fail in the next 4 years is exactly the same as the probability that it would have failed in the first 4 years after you bought it. Okay? That's the memoryless nature. That's called the memoryless nature or the memoryless property of exponential random variables. Okay? And this may be a little surprising for lifetimes, by the way. Right? Human lifetimes are not like that. I mean, so therefore, human lifetimes cannot be modeled as exponential random variables, because otherwise, if we were modeling human lifetimes as exponential random variables, what you were really saying was that the probability of death between 80 and 90 years is exactly the same as the probability of death between 50 and 60 years. Okay? So human lifetimes के लिए or failure, people do model it, and there's failure reliability or ये वाली सारी areas and they deal with this. So you will not be able to use an exponential random variable to model human lifetimes. However, exponential random variables are used to model electronic components. ठीक है? And that's fairly accurate. कि अगर 2 साल के अंदर fail नहीं हुआ ना, तो फिर ठीक है, you're good enough. Right? So that's the same as अगले 2 साल में failure की probability उतनी है जितनी पहले 2 साल में. Okay? जी मौसम.
सर थोड़ा सा ये काउंटर इंट्यूटिव लग रही है memoryless property को associate करना breakdown of electronic goods से.
So what the first thing I want to point out here is that the memoryless property is not necessarily a character of electronic components per se. Okay? So memoryless property is actually a character of an exponential random variable. And if you're modeling a lifetime of anything with an exponential random variable, that means the memoryless property will hold. Okay? So the memoryless property, अगर आप practical significance को भूल जाएं, mathematically speaking, exponential random variables के अंदर एक inherent एक memoryless property होती है, right? अब physically speaking, ऐसे जितने भी चीजें हैं जिनकी lifetime में ये memoryless property होगी, we can use exponential random variable to model it. Why is an exponential random variable a good model for electronic components? That's a different debate altogether. right? And is it counterintuitive? Yes, it is counterintuitive. Lekin you may be able to come across counter arguments for that, and maybe we can continue that in this discussion forum. Okay, Mohsen? So maybe you can dig up some material here on why like exponential random variables or exponential PDFs are a good lifetime model for electronic components and post it on the discussion forums. Discussion forums में मैंने 3-4 चीजें और भी post की है. याद रखें कि बहुत सारे एग्जाम्स, दैट्स व्हाई आई एम थिंकिंग, तो एग्जाम प्रॉब्लम्स वहां से मैं निकाल लूंगा, ठीक है. नो, नॉट अ लॉट ऑफ पीपल आर एक्चुअली following that discussion. Okay, any questions?